Welcome to the Science Seminar brought to you by the Department of Chemistry and Physics. This is an important part of your education. Hope you realize it's beyond the classroom. It's where science is really happening.
For the fun sciences.
What's that?
For the fun part of science.
Yeah, this is the fun part of science. This is stuff that applications of what you learn in the classroom. And so we're really happy here that we can bring you these speakers that we have this semester. So I would encourage you to check out latu.edu/science seminars and look at the whole list of things that will be happening this semester in the science seminars. And today it's our real pleasure to have as our keynote address this semester Dr. David Hilton from Baylor University. He's happy to be here because Baylor is a sister Christian university, and he wants you guys, after you matriculate here with your bachelor's degree, to come over there and do a master's or a PhD. Right. They would prefer PhD, but there's masters there as well.
Masters as well.
Yeah, yes, masters as well.
I'll deal with the university's issues.
So just to tell you a little bit about David here. He's not a native of Texas, so we won't hold that against him.
I've lived here 2 different times in my life, so I came back. So
Came back.
it's kind of work in my favor, at least.
Yeah. At least he's in Texas now, right? So we're good here. And he spent some time as a postdoc researcher at Rice University here in Texas. He also was a graduate student at Cornell. He also did a postdoc at Los Alamos National Lab. You guys know all about Los Alamos there.
I've had a tour of the South and the Southwest over the years.
Yes. And so after seeing the whole world and everything else, he's chosen to live here in Texas. So we're happy there. And if you want to speak with David, specifically about things after the seminar, the place to do that is at lunch. Okay? So if you're interested in graduate school, even just a little bit interested in graduate school and how it works, come to lunch with us. One thing that most undergraduates don't know is that if you get a degree in the sciences, in chemistry, biology, physics, or engineering, you get paid to go to graduate school. Yes? It becomes a job for you to do, and it's an exciting job and it's an exciting adventure. So don't think of graduate school as just more undergraduate school. It's very different. And it's your job now as an undergraduate to learn about graduate school, because it may be in your future, or might not be, but you don't know unless you learn about it. So today David's going to tell us about his research and a little bit about the graduate program at Baylor. So let's give him a warm.
Yeah, I'll talk a little bit about our grad program at the end, but let me just piggyback a little bit on that, because I know that this room is not all physicists, which is great. I'm not either. So my undergraduate degree is in optical engineering from the University of Rochester. I stayed to get a master's degree thinking I wanted to get a better job, and then decided that, hey, I like being a student, let me stay a student forever. And I ended up switching, and I ended up going to engineering physics as my PhD. So I've floated around different departments. When I go to Los Alamos, I'm actually in material science there. When I worked at Rice, I was in electrical engineering. And then finally, when I joined the faculty at the University of Alabama, for the first time in my life, I actually had an office in the physics building. It was a little strange. So I'll talk a little bit about grad school again, but I want you all to consider that you haven't made a decision yet. So maybe you're a physics major, a chemistry major, or something, a computer science major. There's a lot of cross-disciplinary opportunities in grad school. So you don't have to be a physics undergraduate major. I wasn't. To be in a physics program in grad school. So there's a lot of flexibility with that. So if you're thinking about grad school, I'd love to talk to you about Baylor's program. We're a Christian institution as well, but I'm also willing to talk to you about grad school in general, because I've been at a bunch of different universities across the South, the Southwest, the Northeast. I think at some point my family could call my cell phone number, but didn't actually know which time zone I was living in at that point, because I'd moved around so many times they lost track of me. So if that's something that's of interest to you, come on to lunch, because I'd be happy to talk to you about not only what is available at Baylor, but beyond all of that. In the short term, let me talk about the fun stuff that I do. So I am undergraduate in optics. My PhD is in engineering physics. I'm somebody that wants to use light as a research tool to understand materials. And specifically, the phrase that's being used right now is quantum materials. So I'm not interested in designing silicon. We know how that works really well. I'm interested in designing materials and providing data to people that grow materials that will be the materials that will be part of quantum computers in the future. Right now, a lot of quantum computers use these little macroscopic squid coils that are about roughly this big, and they coherently couple them all together. But that's the equivalent of a transistor in all of that. So when you talk about some of the quantum computers out there, you're talking about hundreds to a couple hundred different quantum bits. And to give you a scale of all of that, this is 2.3 billion transistors in the computer processor on all of this. So the scale is tremendously lower than it needs to be. And so if you're talking about taking structures that are on the order of a centimeter and putting billions of them together, now you're talking about gigantic buildings, or you're talking about new technologies that can make things smaller. So I want to talk in my talk today about a couple different materials, one of which is we're trying to understand how to build better materials for the radios in cell phones. And I'll talk a little bit about that. And then this two-dimensional material that we look at, this is what's called a quantum well. And what we're interested in there is learning how to manipulate these materials, not as a qubit, but in the ways that we would need to be able to manipulate them as a qubit. I'm not really a devices person, so I'm not actually trying to build a widget. I'm trying to get the physics behind so that people can build widgets. And then talk a little bit about what we do, and I may cut this part because I'm not certain I'm going to have enough time for that, but talk a little bit about what we do of looking at materials in very high magnetic fields. How many people in the room have had an MRI done? Okay. Typically, those are about 1 to 2 Tesla, depending upon the resolution of the instrument, and they're sliding you into the middle of a superconducting magnet. We deal with 25 Tesla magnets at the National High Magnetic Field Lab. So these are quite a bit bigger than all of that. I got the numbers down, but it's 34 megawatts of power. We go through electricity in a week running that magnet that the average American goes through in a year. I don't pay that electric bill, fortunately. And then I want to talk a little bit about the lab and some of the future directions. And so it's a spin-off of this particular research project here. And I'll talk a little bit about where we're going with our research program. So for next generation communications, for those of you that have a relatively recent cell phone, actually I think the picture is here. This is the issue. So the more recent cell phones have a second radio on them. If you've got an iPhone, it's actually under the volume rocker. There's a second radio there. And it's starting to look at emitting wavelengths that you would call the traditional microwave. And so the reason for this is we're starting to run out of frequencies to have all of you have a cell phone, all of you have a watch that's connected, and then have the population densities that we have. We're starting to run out of the frequencies to do all of this. And so they keep raising up to higher and higher frequencies, and that requires new and new technology. And so this is a prediction from a couple of years ago about basically they're predicting something like a 49 times increase in the amount of data that's necessary to be on cellular networks. For those of you that watch Netflix while you should be watching our lectures, you're why. It's getting Netflix and getting all of these videos pushed through the cell phone networks that's a lot of the reason why we don't do that during lectures. We're interesting to listen to. But if you do, that's why. And so for 4G and 5G networks, we're looking at frequencies that are typically on the order of a gigahertz. It's very hard to see because it's black on black, but there's actually a slot 5G millimeter wave radio. This is actually my iPhone, it's an iPhone 13. And then the next generation from all of that goes up higher and higher in frequency. And the problem from an engineering perspective is this is a silicon germanium radio. People have been making them for a long time. For a variety of reasons, these don't scale very well to the very high frequencies. They're not fast enough, they can't be modulated fast enough to be able to work within these sort of couple hundred gigahertz to 3 terahertz frequencies. The other problem with them is a lot more practical. So for a county of this size, there are cell phone towers in here, and there's several different cell phone towers in this county which service all of you. And so you can be several miles away from that cell phone tower, and your radio can still reach there. Once you start to get up to these frequency ranges, the next generation antenna are going to be on top of this building. Or there are going to be several of them on this campus in order to be able to serve all of you because they simply don't make it far enough in the atmosphere to be able to serve an entire county from all of this. So not only do we need to find new materials that are fast enough to do all of this, we're going to need to deploy a lot more towers. We're going to need to deploy a lot more sources of all of these, because once you get up into these wavelength ranges, there's a reason why we didn't start with those wavelength ranges and those frequencies, is they don't make it as far into the atmosphere as traditional radio does. So we need technologies that can be deployed. We also need technologies that can be cost effective. No one wants to see their cell phone bill jump by a factor of 2, although basically we do anyways, but we don't need them to have a reason to double it even further than all of that. So we want to come up with new materials, and specifically we're working with the University of Delaware and Joshua Zeid's group on some nano-engineered materials. So the types of experiments that we do, I'm interested in the dynamics of materials. So I want to take a system, I want to use a short pulse laser to kick it away from equilibrium. I want to put a whole bunch of energy into the system, and I want to watch the energy get out of the system to understand how quickly I can modulate these materials. And so the types of lasers that we use are called titanium sapphire lasers. You've probably never heard of them before, unless you've heard me give a talk before. So these are scientific research tools. Titanium sapphire emits at 800. So if you were all looking at a laser beam without goggles, which is not healthy, so please don't do this, but if you all looked at this, it's a very dark red. If you're red-green colorblind, you don't see it at all because you're missing that cone. But if you are able to see red, it's a very dark red. It's not a color you're used to seeing because it's right on the edge of what you can visibly see from all of this. And so the titanium sapphire laser emits at 800 nanometers. In this particular system, it's a laser that's not on all of the time. It actually emits pulses. So everyone's heard of a nanosecond. So it's a billionth of a second. 1,000 times faster than that's a picosecond. And 1,000 times faster than that's a femtosecond. So it's 100,000th of a billionth of a second long. These are these, and we're looking at 100 femtoseconds for these pulses. So these are extremely short pulses that come out of this system. And relevant to materials, that time scale is the right time scale to talk about an electron being on one atom and moving to its neighbor. So I'm able to see these very basic processes inside of materials, and I'm able to turn how a material conducts electricity into hopscotch, and be able to see the time dynamics of how these materials and these electrons move inside of them on those very fast time scales. No detectors work this fast, so we've got to find a way around all of that. And so this is very much like stop motion photography. I take the pulse, I split it in two, so part of it travels down one path and connects to my detector, the other part travels down the other path, and then I put my sample in the way and I make changes to how that one path transmits the light. And this one path here to the detector is exactly equal to the path to the other one so that they arrive at the same time. And so I'm actually able to use something very much like stop motion photography, where I will do an experiment that will give me one point in time, then I'll make one of the paths a little bit longer, and I'll do that experiment, and then it'll tell me what it looks like 100 femtoseconds after I excited. Then I repeat the experiment 200 femtoseconds, and I can stitch back together all of these dynamics by using this process that's very much like stop motion photography. I take snapshots of the experiment, and then I repeat them over and over again and stitch everything back together again. That's because there's not a detector fast enough that can ever see something that lasts 100 femtoseconds or anything like that. So it's sort of ironic. I'm doing all of these measurements. We call them ultra-fast measurements, but typically each data set takes us 2 to 3 hours to do. So it's a little bit ironic because we're doing things at a really fast time scale, but it takes a very long time to do that because of the limitations of all of our detectors. So this is typical data that we get. So this is a little short terahertz waveform that we get. This is one cycle of the electric field, and this is roughly about 100 femtoseconds long. And it consists of a wide range of frequencies. So we've actually got frequencies here from 300 gigahertz or 0.3 terahertz all the way out to a 10,000 gigahertz or 10 terahertz. And then for a lot of these experiments, I'm going to take a second infrared beam, push the system away from equilibrium, and then watch how this other beam transmits through. This is the type of experiment that we call a pump probe experiment. I disturb the system from equilibrium, and then I start watching how the dynamics take that extra energy and move it back out into the substrate or something along those lines. So data typically looks something like this. I've got before my pump pulse arrives, and then I see a very large drop in transmission, and then I watch the dynamics as it recovers. Excuse me. And so the thing that I'm interested in here is, I'm able to change the wavelength here. I'm able to change some of the frequencies here as well, but I'm actually interested in how quickly this system recovers. And so the system will drop off very quickly, and I'm actually interested in the kind of decay time and the amount of time that it takes for the energy that I put into the system to get back out to equilibrium from all of this. If I want to talk about building a switch out of things, I've got to put energy in and out of systems quickly. So this is sort of a lifetime that limits is how fast I can modulate something. And this is something in this material system that we think we can engineer. So the material is a little bit complicated. So the base semiconductor here is gallium arsenide. So if you look at the periodic table, I've got gallium here and arsenic. I always struggle to find for sensitivity reasons. There we go. So I've got gallium arsenide. That is a very common semiconductor. This is what you're looking at here is a gallium arsenide laser. That's actually a lot of optoelectronics are built around that. So this is a very common material. But it doesn't work very well with some laser sources. So we actually want to dope it with bismuth. So bismuth is here. And so it's actually taking some of the arsenic out of the material and putting bismuth in there. What this tends to do is to shift the absorption edge to longer wavelengths. And that's what we wanted to do with all of that. But you can only get a couple % of bismuth to go in. It's actually not a material that wants to grow into it very well. I was wondering if somebody could give me some water before I lose my voice. I'm sorry to ask, but I can tell this is coming. Thank you very much. I appreciate it. So from the engineering, we start off with the base material of gallium arsenide. A little bit of bismuth is built into all of that. And that basically takes the band gap, the edge, and the absorption edge and makes it smaller. We're actually aiming for something even smaller than that. So my collaborator at Delaware has also learned how to grow erbium arsenide into all of this. And so erbium is here on the 4F band along with arsenic. And so that'll form a compound and create these little puddles of erbium arsenide in the material. And to be able to actually engineer the material. And so this looks very much like a background of gallium bismuth arsenide. And then like all of the chairs in the room, they've got little puddles of the erbium arsenide. He has full control over the density of them, so he can change the spacing between all of the chairs, the spacing between all of the rows on all of this. And so he's got a lot of engineering control over how he builds this material. And I can tell I'm not gonna have a voice for much longer, so I apologize for that. And so we're gonna use a model here to describe this. And so in some cases, this is a more complicated thing where I need it for. Thank you very much for that, I appreciate that. I should have known better than to talk without water these days. Was it ragweed that's in the air right now? I don't know what's in the air right now, but I want to burn it all. Oh, I hate it, I hate it. I want to burn it all down. I don't know what's in the air right now, but I'm going to burn it all down. Okay, so we have an approximation here. So this is actually a very complicated structure, and the mathematics are a little bit too complicated to come up with. So we have this system that's basically a 3-level system where I've got an excited state, I've got a ground state, and then these erbium arsenide states sit roughly mid-gap from all of that. So I'll take the complicated electronic structure of the erbium arsenide doped gallium bismuth arsenide, which is a mouthful, and replace it with something that's a little bit simpler in terms of the modeling and calling it a 3-level system. And so what we do, we optically come in with an infrared pulse. We have full control over the wavelength, so we can pump into 3, we can pump into 2, or we can pump below 2 with this, depending upon the wavelength that we choose and the photon energy that we choose. And then we're watching how the system, if I put the energy in 3, would relax back down to 1, or how the system might relax from 2 down to 1. And it's these erbium arsenide nanoislands that our growers have full control over, so they can control the pitch of them, they can control the diameter of all of them, and they've got actually a lot of control in the engineering. And it turns out we've figured out that that actually tunes these lifetimes that we're interested in, because they very much act like if you were walking around this room mobile, but the first time you get to a chair, you have to sit in it. So it depends upon the density of chairs as how quickly everybody would be sitting down from all of that. That's a similar idea to all of this, but we're using these erbium arsenide nanoislands. So for the math for all of this, we're interested in understanding the population in 3 and the rate of change of all of that, where the population in 2 and the rate of change are the population in 1. And so the rate of change from 3 down to 1 has a rate constant, and it depends upon the population. So we can add terms, and we can build out a rate equation model based on the idea that whatever the rate of change is depends upon the population and these rate constants that we want to get from our experimental data. And then we're photoexciting, in the first set of experiments that I want to talk about, we're photoexciting from 1 up into 3. So we're taking, with a pump, with a laser beam, we're taking population out of 1 and moving it up to 3 as a result. So we've got these rate equations, depending upon the pump wavelength We're either pumping into 3 or we're pumping into 2 with all of these, but these are solvable equations. I know that not everybody in here has had the level of calculus from all of this, but these are relatively solvable coupled differential equations that you can come up with exponential solutions for all of these. And so we can actually do all of that math versus something that's with a band structure generally takes a very large computer and several days to run the math. This is something that even as an experimentalist, you and I can still do. But these are actually solvable equations, and we're able to model all of these and extract what we're interested in are these rate constants. So if I put energy up into 3, how quickly does that energy dissipate? Because that 3 might be an on for a switch, and 1 is off, and I want to be able to switch it on and off quickly, so I need to figure out the rates of how I can move all of this energy. And so all of these look like these sort of exponentials where I've got these rate constants k. And so we end up fitting to a model that looks something like this. So it's experimental set of data here. We've got a t equals 0 point, we've got a drop off, and then a recovery. This drop off here, I'm interested in the amplitude. How quickly it drops off is a function of my instrument. That's actually as fast as I can modulate something with my instrument. So there's no real physics or science in that lifetime there. That's a function of the instrument that I'm using to take these data. But again, what I'm interested in here is this recovery time. So I've got a plot here of the amplitude. That's this piece here. So that tells me how much I'm able to modulate from all of this. And then with this lifetime, here's the plot of the recovery times. And this red region that I'm highlighting here is when I actually photoexcite directly into these erbium arsenide. So this is a good idea of how fast I'm able to modulate and use these erbium arsenide nanoislands to modulate from all of this. And so we've got only one data point within that wavelength range. We're coming back to do a little bit more data on all of this, but there's actually a pronounced dip in the modulation time for something like this. The great thing about where we're able to place all of these is this wavelength corresponds to 1550. And 1550 nanometers is not a wavelength many people have heard, but it is the fundamental wavelength for all of fiber optic communications. So there's a ton of lasers that are built of erbium arsenide, erbium doped fiber amplifiers. And so there's a ton of these lasers buried in all of the cables under the oceans that get you the internet from Europe to the United States. When you pick up the phone on your cell phone and that phone call ends up getting picked up by a radio tower, it then spends the majority of its life in an optical fiber underground to get to the radio tower to the person that you're talking to. And so the entire fiber optic backbone is based around 1550. So this is an important wavelength range to look at because we would be able to, with a switch like this, leverage everything that's already going on with fiber optic communications. I don't have to invent new lasers, I don't have to bury new lasers. I'm going to be able to use this type of a technology to piggyback off of what's already there. So that's going to make it, hopefully, somewhat less expensive to do. So that's sort of the idea of engineering materials. And so what we do with all of this is I do the spectroscopy of all of this, and then this data goes back to my collaborator, and he figures out how to do new things. And so as we understand better the function of these erbium arsenide nanoislands here, I can feed that information back to the people growing. We could be talking, we're not, but we could be talking to people building switches out of all of this. Again, I don't do devices, I just do materials physics, but it's these sorts of lifetimes and amplitudes would be the type of information you would need if you wanted to be an electrical engineer and to start to build radios out of all of this. So the next experiment that we do, this is more quantum physics directly. And I want to understand how to manipulate materials and to manipulate coherence in materials. So what's coherence? So that's, excuse me. Before I start talking, thank you very much again, I can tell this is coming. I want to be able to put materials in coherent states. And so I want to be able to have a large number of these systems all in a particular quantum state, all in phase. So the nice distinction there is if I stopped talking and you all started talking and you had completely independent conversations, there'd be a lot of volume in this room, but there would be just a whole bunch of sound. It would be very difficult to pick out an individual call because you're all having separate conversations. And so that would be an incoherent state like this. A coherent state is if I asked you all to say the Pledge of Allegiance. You'd all be saying the exact same words, and it would all be in phase. You'd all be saying the same things at the same time, and the collective would add up into one ensemble that's saying the same words at the same time. And so that's a similar idea to coherence. I want to take a system like this two-dimensional electron gas, and I want to put everything, and I want to put a whole bunch of electrons all in the same quantum state, and I want them to maintain that quantum state and to all be in synchronization with each other. What tends to happen in these systems is everybody starts off saying the Pledge of Allegiance effectively, but no one says it at the same rate. So by the time you get halfway through it, everybody's still saying the Pledge of Allegiance, but no one's saying the same words at the same time. So you're all doing the same thing, but you're starting to drift out of phase because you're saying one word, you're saying a different word, and the entire signal gets lost as a result because the coherence of all of you gets lost as a result. So cyclotron resonance spectroscopy, what we do here is we have a material. We apply an external magnetic field to all of this. And so for my external magnetic field, I know that I create a force, one from the electric field that might be inside of all of this, but I also create a force if my electron is going this way and my magnetic field is going this way, I'm going to create a force that's perpendicular to both of them. So I would end up creating a system here that basically all of these electrons are going to be tracing out these circular orbits. They're called cyclotrons. And so that's what it looks like when you talk about the laws of classical mechanics. When you start looking at quantum mechanics, well then you start with Schrödinger's equation, and it's a little bit different. So in classical mechanics, I would be allowed to have any radius or circumference of that circle. In quantum mechanics, I essentially am only allowed to have circles where I've got an even number of electron wavelengths from all of this. And so I'm only allowed to have certain electronic orbits here and only allowed to have certain radii for all of this. And so my energy here can be whatever I want it to be, but here it actually becomes individual levels of energy that I'm allowed to have because I'm not allowed to keep continuously turning it up. I'm only allowed to do it such that the circumference is an even number of these wavelengths. And so it becomes quantum as a result, and this is something that we like because we know how to grow these two-dimensional layers very well. Again, gallium arsenide, not an accident. It's the second most common semiconductor to silicon in science, but also in manufacturing. And so we do a lot of systems. Again, this is a gallium arsenide laser right here. A lot of technology is built around it, especially in optoelectronics. So we know how to grow very high-quality gallium arsenide. And these two-dimensional layers are relatively straightforward to grow as well. So this is an easy, high-quality material that we can get. And so this has been done before. There's a wide variety of materials. Some of this goes back to the early 1980s. And so this is mobility and carrier concentration. So this is the number of electrons that we have. And this mobility is a measure of how clean the sample is. This is a relatively dirty sample with lots of things in it that are not gallium arsenide. This is, on this end, this is a material that is, these numbers are getting close to about the most perfect piece of gallium arsenide with no defects whatsoever. This is what's called the mobility limit of these materials. And so there's a wide variety of these that have been looked at. We look at basically two different materials here, one that's a little bit dirtier and then one that's a little bit cleaner. It's actually, they're both defect-free. It's the width of the well here. And so what do we do in our experiments? We've got these levels, we've got these cyclotrons here. I come through with my light and I create a transition, I create a superposition, and a coherent superposition between all of there, and then I watch the system as it decays. It's very similar to what I was talking about in the erbium arsenide, gallium bismuth arsenide sample, except for here, I'm not interested in dropping back down, I'm just interested in the extent to which coherence is lost. Again, the analogy there is the extent to which, if you were all saying the Pledge of Allegiance at different rates, the extent to which it would muddy out, even though you're all saying the same words. And looking at this coherence. And so the coherence can be lost when energy gets transferred from these electrons into the lattice. And so there's a decoherence time that I want to get to. There's also a secondary process here where the system spits light back out again. It's called superradiant emission. And so I want to take this superradiant emission, which is known physics, and remove it from my data and understand how I'm decohering the system. So the application for all of this would be, again, we would use a material like this, create this two-level system, create this superposition. People could build quantum computers out of all of it. Again, I'm not a devices person, so I'm not doing that, but I'm interested in the physics that would be necessary to do all of that. And so the type of data that we look at here, these cyclotron oscillations come as a function of wiggles in the electric field. So I've got excitation here, I've got 3 or 4 oscillations in the period here. These are actually in the wider quantum wells, these are actually longer oscillations here. There's actually a second pulse in my system because of a satellite reflection, and so you end up seeing the spike appear here a little bit larger. We're able to model for all of this in terms of the transmission of the data. And so if I look at this decay time here, so if this is a sine wave that's decaying in time, I'm interested in the decay time on all of these, and that's what I've got as a plot of here. And so I've got two samples here. I've got a 30 nanometer quantum well and a 12 nanometer quantum well, and I've got sort of these decay times here as a function of temperature, all the way down to 400 millikelvin in this case. And what I'm interested with the data and the analysis on the next slide is below about 1 Kelvin, I see a rather strong increase in this decay time. And so I see a lot longer persistence of this coherence that I'm interested in, versus in the very narrow quantum well, I see a much shorter persistence in this coherence. And so the experiment here, I have to remove this light emission time from all of that, but this is a fairly well-known way to do all of that. And so I get this decoherence time, which is derived from my experimental data. And so I'm seeing this very dramatic increase in the persistence of this coherence below a Kelvin. And so you might think a Kelvin's a difficult temperature to get to. Yeah, it is. So you can get down to 77 Kelvin with liquid nitrogen. You can get down to about 4 Kelvin with liquid helium. And you need something called helium-3 to get down to temperatures that are this low. And so if I was talking about this 20 years ago when I was in grad school, this would have been a deal breaker for devices. They're building quantum computers at these temperatures right now. If you've ever seen Google's quantum computer and they've got this big gold thing that's hanging in the middle of the room, that's exposed to air. That's a dilution refrigerator. I'll show you mine. I have one of them at Baylor right now. I'll show you mine. But those are all being held down at millikelvin temperatures. And so this used to be something that was extremely difficult to do. It's something that's becoming a lot more common. So even though a Kelvin seems like a very cold temperature, it is. This is now actually a practical device. So you're not going to own any time in the near future a quantum computer on your desktop. This is going to be a user facility. The federal government will own one. Various federal governments will own one. There will be Google, Honeywell has something that's available for people to use. So these are going to be user facilities. So you have a calculation you want to do. You want to run it on one of these. You submit it to a government lab to do it, because they're going to be too expensive for Baylor or the turnover for any of the universities to have any time in the near future. But these are things that are going to be available probably in the next 5 to 10 years. They'll be able to be scaled up enough that people will be able to submit jobs to them to use these sorts of computers. I don't know that they're ever going to replace this technology. I don't know how to do that right now. But these are things that you can currently rent time on Honeywell's computer, which is in the Denver area. It can't do a whole lot right now, so you're sort of playing around and figuring out algorithms and stuff like that. You can't do large-scale computer calculations on it right now, but you can currently rent time on some of these companies' computers. At the very least, to start to gain some experience for your company. That's where this is all headed. So 1 Kelvin is a little bit cold, but it's actually not impractical anymore to get to. So with these data here, we went to some friends at the University of Central Florida. So I talked to you about, in the previous experiment, the 3-level system calculation that I can do on a personal desktop computer. There are other numerical solutions to Schrödinger's equation called density functional theory. These generally require days to run on computers and relatively large computers to do so, but there's specialists that do all of this. And so they did some calculations for us to actually model our results. And so it turns out the interesting thing for us is this is the change in how scattering happens. So the electrons move through these materials, and eventually they run into something that shouldn't be there. And so instead of going in the direction that they're going in, they scatter into a different direction. And between those two different quantum wells and these two different results, the scattering dynamics are very different. And so for a cyclotron, I think about I'm tracing out all of these circular orbits. When I get to a certain point in the circular orbit and I scatter, my momentum was going this way, now it's going this way. And so what that does to a cyclotron is, well, I've got to be moving in circular motion here, so if I change the direction of my momentum, then I'm going to trace out a different circular orbit from all of this. So if I think about getting from the top of the orbit around to the top of the orbit again, it doesn't actually take 360 degrees to go around the circle. It takes more than that. And it's this scattering angle that gets added onto everything. And so we were able to actually use this entire model with this sort of scattering dynamics model here. And so we were able to predict a transition temperature right around the transition temperature that we see, and we were able to see this lifetime take off roughly in the same pattern there. And the unique thing here was it was based not on a scattering rate changing, which is how we thought it was, but it was actually on the geometry of how scattering happened. So it gives you a new way of trying to control these sorts of physics phenomena. sort of just said most of this, so I'll skip this. And so this is a calculation that we ran. So this is a set of cyclotrons. The blue arrows are all of those momentum vectors, and they're all pointed in the same direction at t equals 0. And I'm going to have two different scenarios that pop up, one down here and one down here, depending upon the angle that I allow scattering to occur. Both of these simulations that I'm going to show here, they all scatter once a picosecond. So they're all hitting and getting scattered at the same rate. It's just a matter of how effective each scattering is at coming up and dephasing the ensemble. And so if I take a very narrow distribution of scattering angles, then you can see that the entire ensemble, all of those blue arrows are largely pointed in the same direction. So it's all still very coherent here with this exact same scattering rate. So each of these has scattered the same number of times, but because this one I'm allowing the scattering angle to be much larger, I'm able to actually mess up the angle quite a bit faster than all of this. So there's a lot of loss in coherence on this side versus that side because of the changes to the way that I'm allowing electrons to scatter and all of this from the changes in dimensionality. That's a lot to unpack from all of this. I don't know what you do with that in a device. It's basic physics to me. But it was a neat result for us in order to be able to understand what was relevant, and something that we published about a year ago now. It was relevant to how we were able to control decoherence in materials. I think I'm going to skip parts of all of this because I want to make sure I have enough time for questions, and I want to make sure I have enough time to talk about our graduate program as well. So high magnetic field, I'll talk about the high magnetic field part of it, but I'll probably skip a little bit about the MOS too. So this is the magnet that we use in the National High Magnetic Field Lab. Not only do we have cool toys at Baylor, we can borrow other people's cool toys too. It's really a lot of fun. So the split helix magnet, if I were to walk up next to this thing, my head is roughly around where that yellow side is, to give you a scale of all of this. So this thing's about the size of an automobile. It's a 25 Tesla magnet. That is not the strongest magnet on the planet. There are several other ones that have higher fields than all of that. The unique thing for us with this one, I'm an optical spectroscopy person, so there's actually optical windows built into the side of this. Generally, all of these high field magnets are big metal cans, so I really can't get light into or out of them very well. This one was designed specifically to be able to enable the type of experiments that I was just talking about doing. So if you see a few things here, if you see these very large green cables that look like electrical cables, there are 8 of them in and 8 of them out. That's the electrical power supply for all of this, and they're roughly this big in diameter because they have to be to get as much energy into all of this. And so this was a new design for a magnet. They actually patented it. It's called a split Florida helix. It's able to sustain 25 Tesla, so we can ramp up to 25 Tesla and sit there. There are other magnets on the planet that go higher than that. At Los Alamos National Labs, there's a magnet that will hit 120 Tesla, but it'll do it as a pulse because they've got a set of capacitor banks that discharge all of the energy all at once because they can't sustain enough current to sustain 120 Tesla. And so that's the largest, that I'm aware of, the largest magnetic field on this continent. The Japanese have a facility in Tsukuba, in one of their research facilities in Japan. It's a single turn coil, so the coils are about this big around. They're one solid piece of copper. There's a big fan on one side and there's a single loop of copper. It'll be 300 Tesla at the center of all of that when they discharge. And they're all replaceable coils because in the process of putting that much current through copper, you'll also vaporize the entire copper. So you can get 4 shots a day, but you've got to replace the coil each time around. I've never run on that one before. I want to do something on it. I've just never figured out what I can do on all of it. It just seems, I don't know, it seems destructive. It seems like fun. I don't know. I'm sure there's a science reason beyond fun, but it just seems fun to me to do something like that. They also have a prototype that they did. It was trying to scale up beyond 300 Tesla. If anyone wants to see it, email me. I'll show you the paper because it's a hilarious paper to read. They don't actually know what magnetic field they got to. They were aiming at 1,000 Tesla. The problem is they know they went further than that because they had a steel door that was about 1/2 meter in diameter. That was the door for the room to protect the room to keep the field from getting out there, and they dislodged it from its hinges. And so they know that the 1,000 Tesla that they thought they were going to get is probably not sufficient to actually physically move that much steel from the EMF from all of that. So they don't actually know what field they got to with all of that. But it's the only paper I've ever seen where a door taken off its hinges was provided as scientific data. There's some interesting papers out there, but that was one, in my field, that was one of them where like, well, that's an interesting set of data, but I'll take that for a data point. So there's a lot of fun with all of this. So this one, I'm reasonably certain that number is not even accurate anymore because that was a couple of years ago and electricity is a lot more expensive. But at one point, this was $22,000 a week to run. As I said, I didn't have to pay that electrical bill, so that was good. I'm sure it's more than that right now. So it's 34 megawatts of power and about 6.6 kiloamps of current. And when it's running, it's about where that corner is relative to where I am. So you're actually able to run in the room. Why do we do this? And I'm going to skip talking about MOS too because I want to talk about the grad program a little bit. But there's a number of materials, and specifically superconducting materials and copper oxide-based superconductors, where they stop being superconductors somewhere in the 20 to 25 Tesla range in very interesting ways. And we don't understand why they're superconductors to begin with. So one of the nice ways of figuring out how something is put together is by tearing it down and taking it apart. So there's a lot of interest in looking at this class of superconductors, but you need to be 20 to 25 Tesla to do all of this. And for me, I need the optics access to doing all of this. But there's a lot of interest in looking at these materials to try and understand how they are being a superconductor, how they are conducting electricity without resistance, because there's lots of technological applications. All of you that raised your hand and said you were inside of an MRI, you were inside of a superconducting magnet. And so they're able to persist the coil, and there's typically neodymium germanium is a material, but it's a wire, and you're inside of a superconducting magnet, and that current persists forever. They don't have to actually keep driving current to all of it. That current will actually persist forever in the superconductor because there's no resistance. And so there's a lot of interest, and so this was paid for by the taxpayers. This is a National Science Foundation facility. But there's a lot of interest in understanding what happens to these materials in these sort of high magnetic fields, because there's lots of applications. And it always goes back to the analogy that I make. If I want to understand how a car engine works, a good way to do it is to tear it apart and see all of the pieces and see how it gets put together. It's the same thing we do as scientists. I want to understand how something is a superconductor. The various ways that I can stop it from doing that tell me something about how it's being held together to begin with. And so these are all, from science questions, these are all interesting questions about how do I push this way or push this way, what makes things tick. And if I can understand how they tick, maybe I can design things differently. Maybe I can push things differently, how I can come up with new ways of assembling all of those atoms together to make new materials from this. And I have a few slides on MOS too. I'd be happy to talk if anybody's interested in that, but I do want to talk about the graduate program a little bit. So before I go too far, let me skip a couple slides here. And at least thank the people that work in my research group that did all of the work on all of this. And so my grad students, the work that you've just been looking at, are a combination of now Dr. Ashlyn Birch. She's a postdoc, a staff member now at Sandia National Labs. My soon-to-be finishing grad student, Tracy Hastings, he'll be defending hopefully in the next couple of weeks. I've got to get a final draft of his thesis, but he should be defending soon. And then my two current graduate students, Ravi Buklich and Mohan Giri, and then Shabnam, and then I have a Catholic nun that works for me. One of the interesting features of working at Baylor is you have a Catholic nun that works for you in your research group. I never predicted that in my whole life, especially when they were slapping my knuckles when I was a kid. So Sister Mary Peretti, and then now he just left my group, Ted Walker, who was an undergrad who was working in my group, and he's now in grad school at Arizona State University. A couple of postdocs, Biplav Barman and Tenzin Norton, both worked on all of this, and then I have a network of collaborators at various institutions that help me out with various sample growth or calculations and all of these sorts of things. And for funding, I've got National Science Foundation funding, Department of Energy funding, and then Ashlyn actually had a Department of Education grant. Let me talk a little bit about grad school briefly. Well, I still have a little bit of time. So I want to talk, this is sort of specific to Baylor, but it's general in a lot of cases as well, if you're looking to apply to grad school. As you said, if you are in science, you don't pay for grad school. I have a budget. I pay for TAs or RAs, research assistants, or teaching assistants for all of our graduate students. And so we pay their tuition. Baylor, if any of you know, is not cheap. No, it's crazy how expensive it is, but I'm going to cut that part out of the recording, just in case my bosses find out about all of it. But you don't pay for all of that, and then you get paid for a stipend for that as well. So who we are. This is our vision statement for the department. So how do we view ourselves as both Christian and as physicists? We're trying to understand the physical laws of the universe. We're trying to understand how he makes us all tick. And so we very much view our role here as helping to understand how God's universe works and how we can use that for our own benefit. We want to use the types of things that I talk about. I want to build new devices. I want to build new radios. I want to build new computers. I want to use my capabilities as a scientist to help society from all of that. And we are very much a department, unlike some of them, that will not want you stuck in a lab the whole time. Yes, we have lots of stuff to do science-wise, but we are all, one of our faculty arranges trips with Habitat for Humanity. We do lots of science talks as well. We talk about science in the community. Next summer, I've got a summer camp that I'm starting for rising juniors in high school to talk about quantum information science and technology, to try and get more students interested in science. And so we very much view ourselves as part of a broader community, and trying to use the science that we do to benefit our society. And then we're also a program that admits grad students and wants them to finish. It's not always the case. We bring in grad students, about 10 to 15 a year, and we really want to graduate that many a year as well. There are some grad programs out there that bring in grad students and they expect half of them to flunk out. That is not us. We try and have an environment that if you're struggling, we find help for you. If you're doing really well, we push you even harder because we're just like that. But we're somebody that we really want to build a community around this. As Christians, we don't want to be not Christian in the way that we look at things. And so that's sort of our vision statement. It's right off, I picked it right off our website. This is who we are as a department. So if you're applying to grad school, let me give you a timeline. So this link here, that's a QR code if anyone wants to see that. You start an application. The application is supposed to open October 1st of every year. The last 2 years, the computers crashed at the wrong time. So I'm going to say somewhere around October 1st, but I don't want to commit that it actually opens because the last couple of years it hasn't opened quite right. This year, our application is due on December 1st. That is about in the middle of when a lot of these applications are due for a lot of universities. It's typically in November 15th to December 15th timeline. That's earlier for us than it has been in the past. The application, we want to see transcripts here, any other undergraduate institutions that you be at. We want to see a research statement. We want to see what your interests are. We're going to ask for a letter of recommendation from faculty. We read them very well. They're very important to all of us. If you've heard of the GRE exam, we no longer need that. We don't accept that, and actually you'll find most physics and I think a lot of chemistry programs specifically aren't requiring the GRE anymore. It's like a super SAT, but since it doesn't cover calculus, as physicists we don't find the scores in math to be particularly useful. So we're no longer requiring the GRE, and it's becoming very common to not require that. It's $150 you don't have to spend to apply to that program, so that much is a lot of help in that regard. We will start reviewing applications in December. We do Zoom interviews because of course we recruit worldwide. So we'll do a 15-minute Zoom interview with you. It is not grilling, it's not about physics, it's about your interests and your opportunity to ask us questions. We're interested in understanding if you've got research interests, what they are, how they match with what we're interested in doing. We have an open house in Baylor. It will likely be that weekend of February 7th. That's the historical pattern for all of that, where you get to come on down to Baylor, see the research program, meet with faculty, understand a little bit better with all of that. Decisions that we make are going to be somewhere in that January to February timeframe. I don't yet know how many positions we have because I don't know who's graduating. So we'll make position offers as we have them, but they will float in through January and February. Some people will be at the open house with an offer. Some people won't because we don't know for certain that we're going to have a position, but we think we will. So the actual making offers to people is in January or February. We're trying to make that a little bit more standard, but it requires graduate students to be graduating, that spot opening up for us to bring somebody in. Typically, we bring in about 10 to 15 grad students a year. Funding, you are not paying for this. We have a tuition waiver, so we will waive the tuition on all of this. Typically, our offers come with an offer of either a teaching assistantship, or you'll be a TA for for our freshman and sophomore physics labs, or you'll be a research assistant where you're working for somebody like me in a research group doing science. This year, we are paying our graduate students $30,000 a year. That's enough for an apartment and not, struggling to get by in Baylor. Next year it'll be 32. That's hoped to continue to 34 beyond all of that, but we don't know that right now. and there's a little bit of a travel relocation assistance at $2,000 to help people move. Classes, they look very similar for our program. You take math, quantum mechanics, classical mechanics. This responsible conduct of research is a federal government requirement. It's a research ethics class. It's 1 hour a week. And then we have colloquium. And then there's classes into the second semester of statistical mechanics and electricity and mechanics. If anyone's interested in chemistry, there's a set of chemistry classes as well. I'm happy to introduce you to Michael Trixalis, who's my counterpart in chemistry. We also have a material science PhD program that we've just started up. I'm affiliated with it. I'm not part of the program specifically, but David Jacks, the GPD there. Happy to talk about that as well. With that, I will open the floor to questions. Thank you all.
So, who has the most burning question out there? It's got to be a really fast one because we're talking about femtoseconds.
Yeah, right. Right.
Behind you, Garrett.
Oh,
Yes. What's the point of a supercooled quantum computer? Is there like potential for speed or power?
So that coherence time typically is temperature dependent. So, like I was just showing you taking off below 1,000. By room temperature, the decoherence time is 0. So I wouldn't be able to maintain the sort of coherence at room temperature with most materials. So you want to have it down at low temperatures because that makes that lifetime longer, such that I can actually use it.
got one more picosecond question.
What advantages does the gallium arsenide have over like the more common semiconductors?
So silicon is obviously the easiest material to grow in because there's a lot of infrastructure behind growing in that. It's a terrible material to mine. It doesn't actually want to materialize. So if you need something that actually emits light and manipulates that, silicon is actually not a typically good material for that because there's almost no one who's been able to get light out of silicon as an emitter. So gallium arsenide is sort of a material that's its niche, is in terms of light emission, the semiconductor lasers and all of that. That's why gallium arsenide typically exists. Gets some infrastructure built for it, but it's not nearly as much as silicon. It's a cost argument.
Okay, if you've got further questions, you can come down here to the speaker and also join us in the choice room of the Corner Cafe. Let's thank the speaker one more time.